Good evening and welcome everyone. This is Obi-Wan Pez for N Simplex Pachinko. We are here tonight to have some fun, do some math, and hopefully get some homework help or whatever other people want to do. In the meantime, I will be practicing a little bit of what I'm going to be doing for Calc 2, so just give it a little bit of a rundown. If anyone has any questions, feel free to pop into chat and throw them down into just pop them into the chat. I don't have any sort of queue system or anything like that. I'll Megalomorph might be asking some questions about that. So if anyone doesn't know me out there, I am Obi-Wan Pez. I have been a streaming type person for the last year and a half, I guess. No, that can't be right. I've been working on videos for a year and a half. But I've been streaming for something like 8 or 9 months. And I have been teaching mathematics since about 2006-ish. So pretty close to 15 years. And kind of got my footing at a 2-year college about 13 years ago. When I started teaching there, I was given a lot more leeway to try and invent stuff and deeply understand things. So this is kind of where I'm from. I try to help students understand their mathematics much better at a much more deep level, and hopefully I can help you out with that. So if I don't know something right away, I will at the very least try and look it up or do more research over the week and come back to you on Wednesdays. So, generally speaking, I stream math on Wednesdays. I am also a gamer and have been feeding that habit since I was about 5 years old. So, it's been a good time. Been playing some interesting games, stuff with usually a little bit more substance and story to it. At least I try. And lately have been playing have been playing Outer Wilds. Not the Outer Wilds. That's not a thing. So I've been trying to play Outer Wilds, and that is one of my favorite games. Pretty much instantaneously fell in love with it when I started playing it in the winter of 2019, and lately found out that they were coming out with DLC, Echoes of the Eye, and been playing that, been loving it. So we've been doing that for 2 weeks now. We've played for 2 streams on Friday nights. So anyway, if you're interested in gaming during the school year, I am going to be streaming games only on Friday night because I got a lot of other work that I need to get done. Hooray. At any rate, we're going to come in here and look at some of the cool Calc 2 type stuff. It's funny, I'm using this tool, and yet I am completely ignoring the fact that I can, in fact, draw a straight line. Oh, wait, really? Oh, no, it's absolute. Cool. is what I actually wanted. All right, so let's imagine we have a function that looks something roughly like this, and we would like to approximate the area under the curve. That is between -1 and 1, 2, 3. Sure, why not? 4. So if we're going to go from -1 to +4, we have these particular values. And this is going to be our starting point here. This is going to be our ending point here. So there are many different ways that we could approximate the area under the curve. The simplest idea of which is that we could just do the simple Riemann sums that we were doing from the very beginning of calculus. So how do you find area under curves? Well, you could say, well, we want to find a rectangle. Hang on. Let's go with blue. We're going to find a rectangle which fits under the curve. And in this case, we're just going to give a dx, or a width, just of 1. Alright, so, my artistry notwithstanding, in this particular case, we have n equals 5 or delta x equals 1. And here we're just looking at trying to find the area under the curve. Well, this is easy enough to do, but again, we've already discussed in Calc 1 how here, when a function is increasing, we're undershooting a lot of this stuff here. And when we have a decreasing function or a decreasing area of a function, we're overshooting this value and overestimating our actual area under the curve. So depending on the kind of function you have, the overs and unders may end up just kind of canceling each other out. And depending on how steeply this will increase or decrease at different areas. So, you have the standard Riemann sums. And again, Riemann sums can be taken at the left side, like we have here. At the right side, if we were to draw using red here, we basically see that this is just the opposite problem, where everywhere that a function was too large on one side, it is now too small, and vice versa. So, see that this is going to vastly undershoot on this side, while overshooting on the others. Several of the others. Okay, so blue is going to be a left. Red is going to be the right. So how do we describe these things? This is going to be, again, the Riemann sums are given by the summation as I goes from 1 to n of f of x sub I multiplied by, that's your height, and your width is going to be delta x. Delta x sub I, because potentially you could have a variable size in your delta x. We don't typically do that, but, you know, it could happen. Okay, and we also have the midpoint, which I'm not going to specifically go into, but basically it splits the difference and says, okay, at the midpoint of each of these values, we're going to take this function value in the middle of these sections and then we're going to draw our lines in across through this line, which ends up overshooting some and undershooting others on the same area. So each of these sections are both overshooting the area and undershooting the area at the same time. How much depends on the severity of the steepness of the slope and all that good stuff. But this is one way to handle all of these. I should really have copied that function beforehand, before I actually started all this. So, do I risk it? I don't think I want to undo everything and see if I can just copy it, so we'll just let that go. Right, and the midpoint. Okay, so if we want to do something to try to get a better approximation, we're going to have to do something that gets us better intermediate approximations for all these individual values. That's too much. What am I doing? All right. That's as much as we need anyway. So we have this function which, again, goes from -1 to 1, 2, 3, 4. 4, it is just below 1. And up here. Close. It's a guaranteed point, and that's going to go through there. Alright, so we'll just do something like that. Should just freehand a completely different function. It's fine. Far too worried about trying to get it exactly the same. Alright. Oops. So we get something that looks, roughly speaking, like this. Alright, so we go from -1 to +4. And, right, the midpoint was looking at taking the function value at the midpoint rather than at the left or at the right in order to both undershoot and overshoot at the same time in the same interval. So one of the other things that we could do, even if we do keep it as delta x equals 1, and therefore n equals 5 for this particular setup, is we could just take the function values at each of these points, and again, instead of making it this like just rectangles, we could take these and instead make them trapezoids. Because wouldn't it be slightly easier if we drew straight lines between all of these points? So rather than trying to worry about how perfect everything is, let's just embrace the fact that it's not perfect and draw straight lines. And now this approximates the area under the curve much better. There's a lot less undershooting and overshooting. Drawing a straight line between these points is approximately equal to whatever the function is doing between those points. And if you don't like it, if it looks like it's cutting off too much like this one, just change your delta x. And in this case, if we made it a half, right, that would cut it here. And then we'd have one going this way and one going that way. So it would be much better in this particular case. Hey, Superbrain. So this is going to be other numeric methods, numeric integrals. So I'm teaching that section in Calc 2 tomorrow, which is going to deal with trying alternate methods. So eventually, those of you who out there know what we're going for here, this is going to eventually be Simpson's rule. But we'll go one step at a time, go nice and slow. So, in order to get the area under the curve here, we're going to sum up. I goes from 1 to n, as always. The area of a trapezoid is slightly different, so you do have to just watch out for that. This is going to be 1/2 base 1 plus base 2, which in this case, instead of doing base 1 and base 2, right, those are the vertical sides to the trapezoid, which are given by our function values. So this is going to be f of x1, nope, x sub I, plus f at x sub I plus 1. So take this particular function value and take the next function value. Take their average, which is again how you do areas of trapezoids, and then you multiply by delta x, as always, the height of our trapezoid. So base 1 plus base 2, cut it in half, so we're taking essentially a rectangle that is structured at the midpoint of these places. And then, again, multiply by the height, delta x. So when we do this, depending on the function you have, it can do some funny things, but yes. We only ever did it in Calculus 2. So it was at this level where you've already learned calculus, and now we're going back and studying all of the numeric methods and all of the strategies to be able to prove or to be able to solve previously unsolvable integrals. Okay, so if we look at all this stuff and we start looking at what this actually does with all the individual values, what we're going to see is that a is going to be equal to, here we're going to have 1/2 times all of this stuff, and we could probably do delta x at the beginning if you feel like it. It doesn't much matter, right? So delta x over 2 times, and inside the parentheses, for the first term, I equals 1, we're going to have f at x sub 1 plus f at x sub 2. Then for the second term, I equals 2, we're going to have f at x sub 2 plus f at x sub 3 plus, and so this is going to continue on until we eventually reach f sub n, nope, f of x sub n, there we go, plus f at x sub n plus 1. All right, so this is the eventual end of it. What we're going to see is that area is equal to delta x over 2 multiplied by, here we have f of x sub 1, and this is the only instance of this particular thing. But now, interestingly enough, the next two terms are both f of x sub 2. And then f at x sub 3 is going to have a partner in the next term that comes after this. And this continues all the way through until we reach f of x sub n, where we're going to have one of its partners back here, and then it itself is here, and then plus f at x sub n plus 1 is going to be by itself. So like the first and last one are by themselves, and all the ones in the middle have two instances. Put this down a little bit here, I guess. Okay. All right, so 2 f at x sub 2 plus 2 f at x sub 3 plus dot 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 plus 2 f at x sub n plus f at x sub n plus 1. Okay, so this is going to be the trapezoid rule. Yeah, well, we get a lot of really great colors here. So this got to be a custom one, right? No? Okay. Yeah. Looks like a unicorn vomited all over the place. So if we wanted an approximation for this particular function, again, we're going to take 1 f of x sub 1 plus 2 f of x sub 2, 2 f of x sub 3, 2 f of x sub 4, 2 f of x sub 5, and 1 f of x sub 6. And then when we add all them up, we're then going to multiply by delta x, which is 1, divided by 2. Add all of them up, and we get a decent approximation of what the area is under this curve, by finding the area of all of the uh, um, trapezoids. So naturally, right? This is the trapezoid rule. And if you want a more accurate trapezoid rule, again, just like we said before, you can take the middle distance here. You're going to have your delta x and thereby also double your n value. So again, we can draw our straight lines here and here, which again gets a much more accurate picture of this particular curve rather than having to yep. Rather than having to skip a whole bunch here. We could just double the n value, which is having the delta x value, and get a larger or smaller sample size. There we go. Is it always feasible? No, not really. Sometimes you do end up with, you're not able to stress the server anymore by doing, huge number of floating point calculations. So for that case, yeah, you'd probably want to find a different method that works faster and finds stuff a little more simply. Okay, and the area here is approximately equal to function integrated f of x dx from a to b. All right, so what we talked about earlier about needing to use for this one. Oh, okay. So what we need for a better approximation is going to be another way to find some sort of measurement of the curvature here and be able to find the area under that curve. Oh, goodness. All right, so instead of doing a linear approximation using a trapezoid rule like this, what we can actually do is still find all the same points, all the same endpoints, and even if we're still doing everything with just this many values. We can approximate each of these individual segments between each of the points that we find, each of our function values. we can approximate with a quadratic function. So a quadratic function will get this curve represented much more nicely than a linear function will. So just basically increase the degree by 1, right? And you'll be able to figure out something. So we're going to say that the area of f of x dx from, again, x sub interesting. Okay, so this is actually using 2 segments because we have 3 points here, right? So any 3 points will define a quadratic. So this is going to go from x sub 1 to x sub 3 is how we had it before. So this one here, x sub 1 comma f at x sub 1. So this is going to be given by an approximation of the integral of ax squared plus bx plus c dx from x1 to x3. So then what we get here is if we take the integral, we're going to get a over 3x cubed plus b over 2x squared plus cx evaluated from x1 to x3. Is going to be a over 3 multiplied by x3 cubed minus x1 cubed plus b over 2 times x3 squared minus x1 squared plus c times x3 minus x1. Now, in each of these, we actually have an x3 minus x1. So here, we can take out x3 minus x1, and we're left with a over 3 times. I don't necessarily know this stuff right off the top of my head either, so don't feel bad if you don't either. Yeah, I know. But yeah, if you're doing something where the function itself is tremendously large, you don't necessarily want to do anything to it other than sending in individual values, or there is also the potential that you don't have a function and you just have a bunch of data. That's not exactly appropriate for this right here because you do actually have to have like more than just function values. You need to know something about the rates of change. However, you could also come up with methods by which you approximate any sorts of rates of change or like areas under curves for certain spaces if they are discrete, like discrete data points. All right, so I don't remember the cubic rule right off the top of my head, so this is x3 squared plus x3 x1 plus x1 squared. All right, so this is our difference of cubes formula. You got the difference of 2 cubes is equal to the difference between the cubes multiplied by the first one squared plus their cross product plus the second one squared. Alright, plus, this is b over 2. This, we remove the x3 minus x1, and we're left with x3 plus x1. So difference of squares. Plus c. Right, we take out the x3 minus x1. In addition, we've also got a 3 and a 2 as part of a fraction on the inside. So one of the things that we can do is divide by 6. And that'll take these two out. It'll also cause us to have the remaining factors multiplied by all these other pieces. Okay. Oh, right. It should be noted that here, delta x is equal to x3 minus x1. However, this is the span of two areas, so we have to divide by 2 in order to get rid of the second area. So then here, this is going to leave us with delta x over just 3 times, and when we multiply all this stuff in, this is going to be 2a x3 squared plus 2a x3 x1 plus 2a x1 squared plus 3b x3 plus 3b x1 plus 6c. All right, then it should be noted that we actually have some things that can be simplified. So first off, we have right, okay. We're going to combine all the things with like terms. So here we have a 2a x to the third squared. No, x sub 3 squared. Wow. And we look at the other terms which have an x sub 3 in it. Yeah, okay. It's going to be delta x over 3. We have here a all right, we're going to split this into two parts. So we have one a times x of 3 squared, and then also another one underneath it, which we're going to add to different terms in different ways. A times x of 3 squared. Then we're going to do the same with the b. So 3b times x sub 3. On the top here, this is going to be 1 b times x sub 3. Yeah. And then we're also going to add a c value out of our 6c here. So there's 1. Plus, we can also do the same with x sub 1. So ax1 sub 1 squared and a times x sub 1 squared at the bottom. Then we also have a b x1. And I believe that this must be a 2... Okay, next term. I see. We're getting there. Alright, so plus b times x of 1 plus another c. Alright, so then down here we've got a times x of 3 squared. This is also going to be added to other terms that have a's, specifically 2 x of 3 x of 1. And yeah, okay. The other a times x of 1 squared is going to come down over here. That's supposed to be a 2a. Didn't need to scrunch up quite so much. All right. So, a times x of 3 squared, and also an a times x of 1 squared over here. I guess technically that's the same as that one, right? Yeah, that's going to be the same thing. Plus, now we're going to get all of the b's that are left over. So we've got one of each of those. So now we're going to have 2b x of 3 plus 2b x of 1. And then we have two c's that are used, so another 4c, which are going to pop up. Okay. Now we're back on track. This is why I practice. I rarely ever practice, but still. Alright, so for the top one, notice that a times x of 3 squared plus b times x of 3 plus c is just the function, specifically evaluated at x of 3. Plus a times x of 1 squared plus b times x of 1 plus c is also the function at x sub 1. Then in the lower stuff down here, we can take out an a value for that. And then we're left with x of 3 squared plus 2 x of 3 x of 1 plus x of 1 squared, which is x of 3 plus x of 1 squared. In the next bit here, we have a 2b times x of 3 plus x of 1. And here we have a 4c. Sorry. Should also be noted here that x of 3 plus x of 1 over 2 would be equal to x of 2. The average of x of 1 and x of 3, x of 1 and x of 3 is going to be x of 2, the one right in the middle. So then here this could get kicked over, and x of 3 plus x of 1 is going to be equal to 2 x of 2. So here we have 2x of 2, and here we have 2x of 2. And then here, delta x over 3 times the quantity, f of x of 3 plus f of x of 1, plus this is going to be 4a x sub 2 squared plus 4b x sub 2 plus 4c. Delta x over 3 times, this is going to be f of x of 3 plus, I'm going to shift this all the way to the end. So this is going to be a 4 times a times x of 2 squared plus, nope, 4 is gone, b times x of 2 plus c plus f of x of 1, which is delta x over 3 times f of x of 3 plus 4, this a times x of 2 squared plus b times x of 2 plus c is f at x of 2. And so we have the basis for Simpson's rule here. So this is going to be the area. Oops. Ah. Again, integral is going to approximate. Sorry, integral is going to be approximated by this thing. Yes. So you can always do this with... No, that's fine. I don't actually have a formula for it, but it's... I'm sure it's on, like, Stack Exchange or something like that. Because all you need is some, n number of points, and then you should be able to approximate it to whatever degree you want. So if you just shrink your delta x again, I mean, you're always shrinking delta x in calc. So let's see. So if we go x sub 1 to x sub 3 of f of x dx. So yeah, I don't have it. I don't think I've ever looked it up, in fact, but generalize Simpson's rule. Simpson was not the first to discover the rule. Bonaventura Cavalieri in the 1600s, right around 1640, discovered the same, Simpson's rule, as did James Gregory, who published it in 1668. Thomas Simpson, however, discovered it in 1743, or published it in 1743. It's also an interesting fact that, like, he was the one who got credit for it, so, like, how did he miss the other two? If it was more of a local publication or something like that, or like a, within school publication, I could sort of understand it, but, like, did they not submit it to the Royal Society? Especially James Gregory? Tyler Halsey, yes sir. What can I help you with? as best you can go ahead and type it in chat, and we'll try and interpret and get you an answer. So, Daniel Velleman in Mathematical Association of America Monthly 112. When is that? February 18th. Came up with a generalized Simpson's rule. Okay. So really what you're looking for is an equivalent form. So if you have an equivalent form of any fraction, so, 6/7, 8/5, 21/891, nope, seconds. We'll go with that. Right? What we would want to do with any of these particular cases is to say, let's find an equivalent form for this. There could be a reason that you're doing it. So, for example, one reason that you would want an equivalent form is if you're trying to add like 4/3 and 5/6. So keep in mind what parts of fractions you have. Up in the top, you have what's called the numerator. And it enumerates. The pieces you have. And in the denominator, this will state the denomination or sizes. Whoa. Of the pieces. So in the example that I've given here, where we're trying to add 4/3 and 5/6, what you could do, or one thing you could do, is to split up pies into thirds. So here we have 1/3, 1/3, 1/3. Now this is not enough, because we need 4 thirds, and right here we have 1, 2, 3 thirds. So we need an extra one like this. Another third. So altogether, this is 4/3. 5/6. My artistry notwithstanding, will look like this. We got 1/6, we got 1/6, we got 1/6, we got 1/6, and we got 1/6. Totally. Those are exactly the same size. Yep, totally. So here we have 5/6, and here we have 4/3. Now, if you wanted to try to add these together, like, you could just start putting them next to each other, and you'd have 4/3 plus 5/6. But then we want to know, like, okay, really, how much is this? So the problem is that these are different sized objects. And because they're different sizes, you can't directly compare them like that. So in this particular case, what we're going to do is ensure that we can take some of these things and make them have the same size. You've probably heard of least common denominator. So you're trying to find the smallest number that you can split both of these things into to then create things that can be added together, or things that have the same size. So things that are the same, yeah, things that are the same size. So one of the things that we can do is take all of our 1/3 and split them exactly in half. Now when we do that, you notice that each pie is made up of 1, 2, 3, 4, 5, 6 pieces. So now these are each 1/6 of the whole pie. Now this is nice and easy when it's just taking one thing and breaking it into pieces. It's much harder when we start looking at, like, neither of them are similar shapes to the other. We'll talk about that in a little bit. But so now how many sixths do we have when we have 4/3? Well, this is now 1, 2, 3, 4, 5, 6, one entire pie, and 2 more sixths. So 6 plus 2 is going to get us 8 sixths. So instead of 4/3, one of the things that you can do is you multiply the denominator by 2, which is to say that we split each of our pieces in half, and also that causes us to double the number of pieces we have. So if you split each piece in half, you now have 2, which are each half the size. So overall, in terms of this number, nothing has changed except the way it looks. So now we have twice as many pieces, which are half the size. So then here, this is the same thing as now 2 times 4 is 8, divided by 2 times 3 is 6, plus 5/6. And now, since all of these are the same size, right, they're all sixths. Now you can combine them using fractions. So here, this is going to be the same as saying all of them are sixths. And we had 8 in the first group and 5 in the second group. So now that's going to give us 13 sixths. So this is a motivational example, right? Something that makes sense I hope it makes sense anyway. In terms of being able to say, okay, we need to use this particular skill for a specific purpose. In this particular case, we're adding 2 fractions together. And again, we'll do a harder one in a little bit. If we're just doing it kind of in isolation like these and saying, let's get equivalent forms, it does seem a little bit weird, and it does seem like, why are we doing this? But that's just basically saying, like, okay, pretend for a minute that you need the equivalent form that has twice as many pieces, but they're all half the size. Or if we take 6/7 and do 3 times as many pieces, but each one of them is 1/3 of the size. Or 8/5, but again, we have 4 times as many pieces, each of which is 1/4 the size of the starting amount. So in all these cases, we could again build a pie chart essentially that shows us how this all works. Yeah, that's good enough. So in the case of 6/7, hope I can build sevenths here. 1, 2, 3, 4, 5, 6, 7. It's pretty close. It's not quite right, but it's, that's better. That's actually not terrible. All right. So if we get something that is, again, 1/7 each, now we want 1/3 sorry, we want each one to be 1/3 that size, but then we want 3 times as many. So the equivalent form is going to be to take each one of these things. I'm never going to do this with a really fat pen like that. All right, so take each one and split it into thirds. Like that. Okay, one more. Okay. So now what we do is we say, okay, if we'd started with 6/7, that was going to be 1, 2, 3, 4, 5, and 6. So just those, and we're going to ignore this one for the moment. So 1, 2, 3, 4, 5, 6, and each of them is 1/7 of a whole pi. Now, again, we're taking 1/3 of the size. Each of the new pieces is 1/3 the size of the previous one, but they're going to be 3 times as many. So let's show that that's true in this particular case. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So our denominator is that there are now 21 pieces in the whole circle, which is, again, 3 times 7. And then we have 18 of them. So, again, 21, 20, 19, there's 18. So this is 18 of them, which are not blacked out, which is 3 times 6. So this particular thing is telling us that we have 18 of the pieces, 21 of which would make a full circle. Same here, 6/7 means basically the same thing. We have 6 pieces, of which 7 would make a full circle, a full pi. So I'm hoping that makes sense. Let me know. Same with this thing over here, right? 8/5, we could split each pi up into fifths. It's totally fifths. And again, we need 8 of them. It's too much. Where's this going? Something like that. Again, if each one of these is 1/5, then we have 1, 2, 3, 4, 5, 6, 7, 8. We're going to black out these 2, saying that we don't have them. And then we want to split each of these pieces into 4 parts. So in half, and then half again. Didn't like that one. Nope. There we go. Alright, so split them in half, and then split them in half again. Split in half, and then half again. Alright. So again, here, we're going to start at the top here. Curly Yellow, how's it going? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 makes up one entire circle. Again, 4 times 5 on the bottom is going to get you how large are the pieces. So one whole circle is made up of 20 pieces. And here 4 times 8 says we have 32 of them. So here we have 20. And then 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So we now have 32 20ths is going to be the equivalent form of 8/5 that uses pieces which are 1/4 the size of fifths. So they are 20ths. Again, I hope that's helpful to you. And Tyler, let me know if you have any other questions or anything like that. I mean, I see you right there. All right, Pro Fisher, how's it going? What is a transcendental number? Okay, so you have a whole bunch of different numbers that probably you didn't learn set theory in a lot of your classes at school. So I know that it took me until, I mean, we learned a little bit of it in like Algebra 2 and trigonometry, just a little tiny bit, because we talked about complex numbers and what they were, but we didn't really go into it. So I learned it really in college, and then we did a math history course. Let me leave that up there just in case. We did a math history course, which was really great. I loved every little bit of it because the teacher that we had really delved into all of the stories that were kind of behind the mathematicians. And I mean, you all know the stories that are there, they aren't necessarily, well, a lot of them aren't necessarily true, but a lot of them also, like, if that person's story was not exactly the way it was, then somebody else would have found it, right? And in a lot of cases, there are independent developments of mathematics just all over the world. And I mean, because I studied Pascal's triangle especially, hence my channel name, those of you who understand it. So, since I studied Pascal's triangle, I know that Pascal's triangle truly refers only to one application, and that is the binomial distribution of statistical analysis, or within statistical analysis. Prior to him, a mathematician by the name of Al-Jayani was able to come up with the binomial expansion of how you raise a plus b to the nth power and come up with all of your crazy stuff. So he was able to discover a new usage for that triangle, and it became known as Al-Jayani's triangle within the purview of algebra, of doing algebraic expansion of binomials. Prior to him, there was a guy named Yang Hui, who was from China, who discovered the number theory application for Pascal's triangle, in that you just start with a field of zeros, put a 1 at the top, and then expand the triangle downward, adding the two things above it to get to the next thing down. So Yang Hui should be getting the credit for any time you're just looking at a standard triangle that you're just adding, ones all the way down, and then stuff happens in the middle. So he played a game with it. I lost. And so he was the one who first played this game and said, okay, I'm going to add these two numbers to get into here. So there are three people, right? You've got Yang Hui from China. You've got Al-Jayani from Persia, and you have Blaise Pascal from France. So depending on what context you're talking about, you've got three different people who deserve credit for it. But everybody just always says Pascal's triangle. It's, I mean, it's the one we know. It's the one that is in most mathematical books, especially if you're from a European descended school or European descended culture, right? So I'm not even sure that, yeah, I mean, true, but also people need to get over not being able to pronounce names. Oh man, over the last 15 years, I've had some great names that it was like, I need to learn how to pronounce that before day one. I need to learn how to pronounce it before I ever meet the student because my goodness, I cannot mispronounce their name in front of them. Or if I do, they'll at least know that I tried. That one was fun. So, number of years ago, I had a student by this name, and I was like, oh no. Before I came to class, I was like, okay, I need to pronounce this. I need to get it straight in my head. So, so I come in on day one, and I look around, and I go, Jixiang, and she goes, and I'm like, that was a strong reaction, and she's like, I, no one ever pronounces my name right. I'm like, thank you, I'll take it as a compliment. And I since then I have learned some Mandarin pronunciation, not a huge amount, but you know, I learned it especially for her name, and then I started expanding out and being like, okay, here's at least the English letters pronunciation of Mandarin Chinese. I've got that pretty decently down. Anyway, I'm getting far afield here. So when you're talking numbers, you start with the natural numbers. The symbol that goes with was created by, hey, Tyler, thank you very much for the follow. That didn't go off, did it? Okay. Oh, it did. Okay, cool. I didn't hear it for some. Maybe that's why it does it twice. Ah. Okay, so I didn't hear it, but you all did. That's okay. So I think when it went off twice, it was because it was playing into the monitor, and then that causes it to appear on the mic or the auxiliary where my music is also playing. The desktop audio, yeah. So I think it doubles it. I hear it on the desktop audio, and you hear it, and then you hear it again because it was on my desktop audio. Okay, so now I think we're good. All right, anyway. So, natural numbers are also termed the counting numbers. And the counting numbers are going to be those numbers that you use for counting. So you start out 1, 2, 3, 4, etc. So these are intentionally going to be just the positive integers. There are some mathematicians who also include 0 as part of the natural numbers. They will not necessarily say that it's part of the counting numbers, but it's fine. So, these are the natural numbers. The next group out is going to be those that are, 1, 2, 3, 4, etc. But then also expand out further to say, okay, well, we want to also include some other numbers in there, which are going to be the numbers that go that away. So on the number line, we include 0, but also -1, -2, -3, etc. going the other direction. So these are the integers. All whole numbers. All whole numbers in German, which is where the guy who created all this is from. So his name was Georg Cantor. He was a German mathematician from like 1850s-ish. So I constantly forget to look this up exactly, but close enough. Yes. I guess technically like Austro-Hungaria, but it was it is current day Germany. Or Prussia. Forget exactly what they I forget what they called it and when they called it that. So anyway. He is much celebrated in, or was at the time, much celebrated in East Germany. And he has a statue, or, well, a monument to him, which is a cube, which has the major discovery that he made on one of the faces of it. And we'll talk about that in a little bit. Oh yes, they're right. That's your history. You probably know it much better than I do. Okay. I see. So, right, it would be K, right? If it's going to be a K sound, right? Okay. Yep. That makes sense. So, Superbrain, check my translation on this then. Or what the word actually means. So, integers is going to be the doubled Z letter, which is going to be... Wait, we've talked about this, haven't we? Which is the German word Zahlen. Maybe we have done this. Anyway. So the integers are going to be all whole numbers, positive, negative, and 0. Outside of the integers, we have the rationals. So rationals are the first ones that are going to be defined by an algebraic principle rather than just like listing out all of the numbers. Reason being, there's a whole lot of rationals. Specifically, there are an infinite number of rationals between any two rationals you want to pick. So the rationals are going to be given as two integers, a divided by b. Right, so a and b are a member of the integers, and also, well, I guess we're going to exclude b being 0. Right, b cannot be 0. Oops, sorry. Exclude b equals 0. So b can't be 0 because it's in the denominator. Okay, so does Zahlen have any particular meaning other than integers? I know sometimes, like, in English especially, there's sort of a metaphorical sort of meaning. Sometimes words have a... Oh, okay. So just numbers generally. All numbers are like, is it sort of implied that it's really just whole numbers? Element of a set. Okay. Okay, that's fair. So, yep, outside of the integers you have the rationals, which are going to be, again, any ratio of whole numbers. Boop. All right. So, rationals are any ratio of whole numbers. Um, Actually, Superman, probably you know what the correct word is for this. What's the double Q supposed to mean? It's something to do with quotient, but I don't actually know. That's also true. All right, so outside the rational numbers, we have to include numbers. We have to include some other numbers. So, like square roots and things like that are what are termed algebraic numbers. And here again, we're going to define this in sort of a very loose way, and it's going to piss some people off. So, what we have here in algebraic numbers are those numbers which are solutions quotient literally means ratio. Never even thought of it, really. Oh, that's awful. So those numbers which are solutions to polynomials with rational coefficients. So create any polynomial you want. X squared minus 1, right? That's too simple, though. X squared minus 2, for example. X squared minus 2 equals 0. You're going to have to shift the 2 over to the other side, and then take the square root of both sides. You get plus or minus the square root of 2. No, that's fine. All right. So then algebraic numbers include all of those, like we said, phi, which is 1 plus the square root of 5 all over 2. It includes, all of our square roots, our cube roots. Cube root of 17, for example. So practically anything that you want to put in here as square roots, cube roots, fourth roots, fifth roots, etc., are going to fill this space, the algebraic numbers. All right, then outside of that, this next group here. So the real numbers are everything. They encompass everything within this whole space, inside of this whole circle. Yeah, so I think that they're technically complex algebraic. So algebraic numbers originally didn't have the intent to include complex numbers or imaginary numbers because algebraic numbers were defined prior to Rene Descartes coming on the scene and all those people. So the reals get the double R distinction, and this is just any number that you can define as like in any way possible, basically, except any number that was legal at the time when people really wanted this to be a certain way. Again, algebraic numbers don't include the um, non-real algebraic numbers. So again, the square root of -1 doesn't work. These days, you might be able to think of the algebraic numbers as like things that are well ordered, things that have they have solutions in real space. They're defined by real valued functions. So that's being very vague, and it's kind of intentional. But the reals also include everything that has weird patterns. So like 0.101000100010001, etc. So every time that there is a 1, there are an increasing number of zeros between those ones. And there are an infinite different number of patterns that you could come up with. Um, these are non-repeating patterns, typically, because if they repeated, they would be rational. You could come up with some sort of infinity and negative infinity don't exist. They are not numbers. They are ideas. So you could define a real number as like the limit of x as x approaches infinity. But then this doesn't really fall in the real numbers. Like it is sort of a real number, but at the same time the actual limit is not a real number. Because the limit just is infinity, but you can't really do it. This would also include stuff like pi and e, numbers that are defined by series and sequences that, again, don't have a common, yep, numbers that don't have like a common pattern that is super easy to then define as a rational number. If it is a repeating pattern of digits, then it's definitely going to be rational. E is defined as the limit as x approaches infinity of 1 plus 1 over x raised to the x. So this would be kind of a weird way to describe it. So this is essentially your compound interest formula. So 1 plus your rate over the number of compounding periods raised to the number of compounding periods total. That's the number of, this one down here is the number of compounding periods in a year, and this one is the number of compounding periods total, which is the product of the number of compounding periods in a year times the number of years. Pi can be defined in any number of ways. So there are all sorts of cool, nested fractions, for example, like 1 over 2 plus 1 over 3 plus 1 over 8 plus 1 over, and like having fractions that just continue infinitely like this. They can define all sorts of stuff. Yeah, and not all infinite series, right? But some. So the ones that don't have a nice pattern in terms of being able to come up with the same number as like the square root of 3, which you can come up with a particular series which has a limit of the square root of 3. Just like you can come up with a particular series which has a limit of pi, or e, or anything else. Yeah, so then outside of this, this is where we get our complex numbers. And the things that are only in this group here are what are termed imaginary. By René Descartes, a man who was irritated that his contemporary mathematicians were wasting their time on such imaginary numbers when they were trying to solve quadratic equations. Typically, they would come across an answer that looked like, 3 plus or minus the square root of negative 20 over, let's go with like 6 plus or minus. There's a reason. Oh, lost my cursor. There we go. Over, let's say 4. So what would happen here is that normally people like René Descartes and all of the people prior to this looked at this and said, that's not possible. Like, you can't come up with a solution to this. And so they said, well, there is no solution. Solution. All right, there's no solution. And so they were just all the time until the 1500s, people had said, doesn't matter. So then what some mathematicians did was they said, now look here, the 20 is actually a simplifiable square root. So x equals 6 plus or minus we could do this as the square root of square root of 4 times 5, or negative 5. And then the square root of 4 times the square root of negative 5 could also be taken out of this. Right, we can split this up, and then the square root of 4 is just 2. So x equals 6 plus or minus 2 square roots of negative 5 all over 4. And then here we could factor out a 2 from the top, leaving 3 plus or minus the square root of negative 5 all over 2 times 2. Divide out one of those from each, and x is equal to 3 plus or minus the square root of negative 5 all over 2. And so this is an extra few steps, and everybody's just like, why? So Descartes was the one who came up with that particular quotable item. Why would you waste your time with such imaginary numbers? And the name, much to his irritation, stuck. Somebody was like, yeah, that's a great idea. We'll call it that. And he's like, why? Why are you doing this? So complex without R, without the reals, the non-reals. Okay, so you're including the mixed complex numbers in that particular statement. So yeah, it is literally We're cutting out an infinite number of numbers by cutting out one single line, but at the same time, it is the entire plane. Yeah. So with this particular number, you can't just chop out, you can't just square something to cause it to lose the I, or what we call the I term. So these days, we call this x equals 3 plus or minus the square root of negative 1 times the square root of 5 over 2, which is equivalent to 3 plus or minus I root 5 over 2. So the I has its own set of rules. It's easy enough because it's just the square root of negative 1. So if we want to do anything to it, you just have to remind yourself that that's what it is. So yes, you could square that individual term, but the thing is that when you square the whole thing, you don't actually square the I term only. So if we were to take, let's just simplify it a little bit. So 3 plus 2i, right? If we just take 3 plus 2i and square it, note that what that means is you're taking 3 plus 2i and multiplying it by itself, 3 plus 2i. So then here, this is going to be 9 plus 6i plus 6i plus 4i squared. So this I goes away, but you just created another one. So this is going to be 9 plus 4 times I squared is going to be the square root of negative 1 squared, which is negative 1 by definition. So this is actually minus 4, and then plus 12i. So 5 plus 12i. Yeah, I had a friend whose son went into, I guess he's also a friend these days, but who went into pure math, and he was like, I am going to find a field and discover something that no one is ever going to find a use for in my entire life. So he went and he did his work in this particular, subset of mathematics, and he did his doctorate, and he published his work, and within 6 months, somebody had discovered a use for it. He's like, damn it, gonna have to find something new. Yeah, I mean, that's also something interesting. Is not just, when people are working on things that are completely out in left field and you have no idea, like absolutely no idea, what somebody's research might be for. There's going to probably be somebody somewhere at some point, even in your lifetime, and possibly almost immediately, who are going to say, hey, I could use that, and suddenly apply whatever it is that you were looking at and saying, this isn't going to have like a use, and they'll find a use for it somehow. And the number of mathematicians that exist in the world keeps increasing. So the chances that somebody's stuff that once was thought as useless is going to be used, and not just used, but like it's going to thrive in the mathematical space and be applied to something that might actually do something someday, that is, a piece of theoretical technology or a piece of real technology that can be improved by it. It's just amazing to think about how fast technological improvements and the mathematics that govern that is starting to, has been increasing, has been becoming more and more relevant in our, increasingly technological world. It's just wonderful. Love it. Oh man, Saturday morning breakfast cereal. Yeah, I love both SMBC and XKCD. I haven't read them in a long time because I've just been so busy. And then when I do get free time, I don't read their web comics anymore. It's kind of sad, but yeah, they're always worth a good laugh. I mean, can I think of one? Probably not. I mean, I could probably come up with one, but that doesn't mean that it's true either. That's the other problem with, you know, my particular field of expertise, which is teaching. I don't necessarily know all the stories, especially on the stuff that's like higher level. Things that are beyond analysis, things that are beyond, things that are well outside of my personal scope, right? All right, so anyway, we squared this thing, and it got us a particular uh, value here, which was still complex, right? So the other thing that you might be looking at is what would happen if we took both of these answers and multiplied them together. So if we found that we had, uh, let's hmm, now let's just do it all together. So 3 plus I root 5 over 2 times 3 minus I root 5 over 2. So here, right, we got divided by 2, divided by 2. We can just divide by 4 on the outside. Magic squares? Yeah, I mean, it has something to do with like logic and sorting, but I'm not entirely sure like what other usage they would have. So I mean, right, Pro Fisher, that could be an option as far as like what kind of math doesn't have a real world application. Um, maybe magic squares don't. But again, I'm not really sure entirely. There could very well be a perfectly reasonable application for it. All right, so then when we do this, we've got 3 plus I root 5 and 3 minus I root 5. Also true, right? Just having a puzzle by itself could, in theory, be an application. It depends on how you feel about it. All right, so we got 1/4 times. Here we get 9 minus 3I root 5. Here plus 3I root 5. And oh, look at that, they go away. There's your 0 for the i's. And then over here we've got a negative I squared square root of 5 squared. So it's going to be 1/4 multiplied by 9. Here this is going to be a negative 1 multiplied by this negative 1 is going to be a plus. Root 5 squared is going to just be 5. So that is 14/4 or 7/2. So now this is how you can shed any pesky i's that are in here, is if you multiply by what's called the complex conjugate. So if you multiply a complex number by its conjugate pair, you will get a real number back every time. All right. Anybody have any other questions? So this was also another thing was, when we were looking at like how to create rationals is taking the integers and performing an operation on them that does not work with closure. So closure is what happens when you take any particular set and you do something to the numbers in the set and you only get numbers in the set. So the typical definition of like a field within mathematics is that you have a set of rules that apply. So specifically in mathematical fields, you have to have addition, you have to have multiplication, you have to have an identity for each of those operations, and you have to have an inverse for each of those operations. And so when you look at the counting numbers, you start saying, okay, well, just by addition, we clearly have closure. So 1 plus 2 is going to be 3. 1 plus 1 is 2. 2 plus 2 is 4. Any numbers that you add, you're going to get other numbers in the entire sequence. Or in the, well, I mean, it is a sequence, but in the set. Multiplication, similarly. You've got 1 times 2, 1 times 1, 3 times 1, 4 times 2, etc. They're all within the natural numbers. So you will always get the same stuff back. The problem that we run into with trying to make the natural numbers a field is that there isn't an inverse operation for multiplication, and there isn't a reliable inverse operation for addition. So a lot of times when you're doing addition, or well, okay, for addition, there's not even an identity, right? The identity for the additive identity is 0. So you don't have 0 here. You need to add 0 to get back the number you started with. So since we don't have any of that stuff, and please correct me if I'm just spouting nonsense, everybody who has actually taken analysis. It has been 15, 20, oh man, it has been roughly 20 years. Nah, it's more like 18. Since I have taken, what was that class? Abstract algebra. So, and I guess only 8 since I took real analysis. But anyway, yeah. So we don't have an additive identity in the natural numbers. We have an additive identity in the integers, and we also then have additive inverses for the integers, because 1 has an additive inverse of -1. When you add these two things together, you get the additive identity 0. So 1 plus -1 equals 0. Similarly for every other number. So integers are closed under addition, and also the function addition has its identity and its inverse. So we're getting close to the whole like field definition. But then the problem is multiplication again does not. So here multiplication has an identity. It's 1, right? Whenever you multiply by 1, you get the same thing back. But it doesn't have an inverse. Because if you pick 2, for example, the number 2, in order to get back to 1 for the additive, nope, multiplicative identity, the multiplicative inverse is 1 over that particular number. So in the case of 2, the multiplicative inverse is 1/2, which is not part of the integers. So that whole idea that, again, the integers is a field doesn't work either, because, again, there's no multiplicative inverse. But then you get out to the rationals, and now it all works. So we have the additive and multiplicative identities and inverses. We can get all these different values. I can't remember if that actually fits the definition for field, but at the very least, it's certainly a step closer. Like I said, it's been a long time. A field is a set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations on rational and real numbers do. Yeah. So oftentimes we don't say in mathematics that subtraction and division are even a thing. A lot of times we just say, well, you're just adding a negative or multiplying by a fraction instead of dividing. So a lot of times they'll stick with just, is addition and multiplication going to work? And do they have inverses as well? 4 viewers. Oh, damn. Good job, everybody. Thank you so much. So anyway, what I was trying to go for here was that the complex numbers are closed under all operations, basic operations. So again, most of the time we just talk about like addition, multiplication, and exponentiation as kind of the basic operations. But it's not obvious to see this. And again, raising to a power includes raising to any real power. It doesn't even have to be rational or integer power. Any number you want. I guess technically this can be this can actually be a complex number. Right? You can raise a complex number to a complex number. It's really weird and stuff, but it does work. So okay. So one of the things that you can do to show this is, again, start working with any sort of complex number z and show that it has, again, show that it has additive inverses and identities, multiplicative inverses and identities, and exponential identities and inverses. In the case of z, we usually say that this is going to be like a plus bi. And we'll just, z1 is going to be this. Z2 is going to be this. Oops. Keep doing that. So Z1 is A1 plus B1I, Z2 is A2 plus B2I. So you could show that they're closed under basic operations by just performing some basic operations on these, but then we'd also have to worry about like identities and inverses and stuff like that. So if we just add these two things up, Z1 plus Z2, how does addition work? Okay, well this is going to be A1 plus B1I plus A2 plus B2I. These parentheses aren't separating anything of importance, so we can just get rid of them. And then do commutation of addition, or additive commutation, and say that we've got A1 plus A2 plus B1I plus B2I. I can factor out an I. To then get B1 plus B2. I. Plus A1 plus A2. And it should be worth pointing out that when we're doing stuff with complex numbers, A and B are always going to be real numbers. And yes, technically you could just make them arbitrarily also complex numbers, but then it just simplifies back down to the same thing, where you're going to have some sort of complex number again. Okay, so since this is a real number, and this is also a real number, that means that C is going to be, complex numbers are going to be closed under addition. Z1 times Z2. It's going to be A1, A2 plus A2B1I plus A1B2I plus B1B2 I squared. Okay, so then we got real parts. Again, I squared is going to be -1, so this is just going to be A1, A2 minus B1, B2. Plus, parentheses, A1, B2 plus A2, B1 times I. So that's going to be our product, Z1, Z2. And therefore this is closed under multiplication. Now doing something like a1 plus b1I raised to the a2 plus b2I is much harder. All right, you've got to get into this idea of like what are even these imaginary exponents. Like, what does it actually mean to do this? All right, and this is also going to hinge on some mathematical knowledge, particularly Euler's form for yep, for complex numbers. Jeez. Euler form for complex numbers is there we have R, you know what, let's just do this. Z is equal to R times e to the I theta. Or that this is equivalent to R times the quantity, cosine theta, plus I sine theta. So, Euler form uses either of these. Usually, the proof to show R e to the I theta is kind of like sort of a goal. If we take all this and we put it into this form, this says that a1 plus b1I is going to be of the form R1 e to the I times I theta, and that whole thing is being raised to the a2 plus b2I power. So then when we do this, this is going to give itself over R1 raised to the a2 plus b2I. All right, this is going to be e raised to the I times theta times a2 plus b2I. In this particular case, we've got e to the I a2 theta plus b2 theta I squared. And here, adding exponents is going to be the same as multiplying some terms together. Here we get the I squared, so this is going to be negative. All right, so then, oops, that's a theta. we have I a2 theta here, which is going to be an exponent which includes a theta and our I value there. So this is going to be, again, Euler form. This other stuff over here is just going to end up being a constant. I guess you do have to multiply by theta in the exponent, but so I don't necessarily know where to go with this from here, but we can try to think about it. At any rate, when some mathematicians were trying in the 1800s to destabilize complex numbers in order to basically find out whether or not this was closed, there are all sorts of interesting techniques. So I gotta look that up again. All right. Any other questions? Anybody want to see? So anybody who hasn't seen it, right? The thing that most mathematicians were assuming that was that when you took the square root of some sort of complex number, you would get yet another new kind of number. But the thing was that when they did this, if they put it in Euler form, then this 1/2 is an exponent, and it's just going to multiply by this exponent here. So the square root of z, our complex number, is going to be r to the 1/2 times e to the I times theta over 2. So this is also a super important result, was that anytime that you are going to try and take the square root of a number, you need to take the square root of the radius of this particular number, and then also divide the angle of that particular number by 2. What do I mean by that? Well, this is in what's called a polar form. Should maybe have led with that a while ago. So every point on the plane can be ordered into a relationship like this, where we just say that, okay, the function here has an angle, and it also has a radius, which is going to be the length from 0 all the way out to the end. All right. And then when we look at this, again, taking the square root of this particular thing would have the angle. This is going to be a mistake. And we'd also end up taking the square root of that particular value. So we'll just cut it down like there. Arc on theta. This square root of z is instead going to be the square root of r it over to. All right. I think I'm about reaching the limit because otherwise gonna have some fun there. All right, cool. So, if anyone would like to talk about other sorts of mathematics and stuff like that, I will be back on Wednesdays. And I will be back every Wednesday to do math streams, barring any sort of other commitments that are going on. Usually 9 o'clock Eastern US, or what is that, UTC plus 5, right? So that's 0200. And apart from that, I will see you all later. Good luck out there. Gonna start a raid with all right, let's go back to Jason Charles Miller, who is our resident awesome nerdy cowboy musician. And so I'll see you all on next Wednesday for math and Friday nights for gaming. This is Obi-Wan Pez for N Simplex Vichenko. Have a good night.